We have a simple rule to handle polynomials and their derivatives, but now we want to add some more rules that will help us expand the number of functions that we can deal with. And in particular, we're going to talk about derivatives of products and quotients. And let's just start off with the product rule. It's not as simple as you might think it could be. The derivative of a product is not just the product of the derivatives of the factors. However, it is manageable. The product rule says the following. If you have two differentiable functions, f and g, their product, f times g, has a derivative that's equal to f times the derivative of g plus g times the derivative of f. It's the sum of product of each factor with the derivative of the other. Symbolically, you would see something like this. The derivative of the product f times g is f times the derivative of g plus g times the derivative of f. To give you as many ways to picture this and write it as possible, I'd also suggest that you might use u and v instead of f of x and g of x, and if you do that, the rule becomes the derivative of the product uv is just u times v prime plus vu prime. So I'm not saying you have to think of it in all these ways, but pick the way that makes the most sense to you and remember it. I'll do a really simple example. What if I want you to take the derivative of the product of x and x squared plus 1? According to this product rule, you could treat x as being the u in the product rule, and x squared plus 1 as being the v, and the product rule says you take u times v prime plus v times u prime. So you write down u, then you're going to take the derivative of v, then you've got the plus sign, then you're going to do v times the derivative of u. So all that's left to do really is to take those two derivatives and simplify a bit. So the derivative of x squared plus 1 by the power rule is just 2x, and the derivative of x is just 1. So when you've simplified it, you get x times 2x plus the quantity x squared plus 1 times 1. Now, of course, you simplify that a little bit more, and you get 2x squared plus x squared plus 1, which is 3x squared plus 1. Very simple example of the product rule. One thing to notice, sometimes things are written as a product, but you can actually do the derivative more easily by multiplying out the product. And this would be one of those cases where it'd probably be easier just to multiply it out and use the power rule instead of using the product rule, even though either works. For example, because x times the quantity x squared plus 1 is just x cubed plus x, I could just say, well, the derivative of x times the quantity x squared plus 1 is the same as the derivative of x cubed plus x, and then I could use the power rule on each term and get 3x squared plus 1, exactly the same answer, probably a little bit less work. That's a decision you have to make. Sometimes you can see a product and you say, well, I could just multiply it out and do it easier the other way. Sometimes you can do that. Another example. What if I want you to find the derivative of this product 1 over x plus 1 is one factor and x minus 1 is the other factor? Well, the product rule says u times v prime plus v times u prime, but you also have that 1 over x sitting in there. So it's probably a good idea to go ahead and rewrite the 1 over x as x to the minus 1 before you even get started. So that product's going to look like the quantity x to the minus 1 plus 1 times the quantity x minus 1. And then the x to the minus 1 plus 1 is going to be the u, and the x minus 1 is going to be the v in the product rule. And so you'll get u times v prime plus v times u prime. You've got to take the derivative of v. V is just x minus 1, so that derivative is 1. And you've got to take the derivative of u prime, and you've got x to the minus 1. So by the power rule, that'd be minus x to the minus 2. And of course, the derivative of 1 is just 0. Practice makes perfect. Do these problems several times until you can do them easily without making any mistakes. Now, you might simplify that sum. You could take away the times 1, and you could multiply through by the minus x to the minus 2. Now remember, when you're multiplying with like, if you multiply out here this times this and this times this, you're going to end up with an expression like this, and it's an understood 1 exponent. But when you're multiplying with like bases, you add the exponents. You'll end up adding the 1 and the -2. These are the sort of algebraic things you need to focus on and practice until you don't make those careless mistakes anymore, assuming you are making any. So you've got that x to the -1 plus 1, and then when you multiply x times minus x to the -2, you get minus x to the -1 when you add those exponents. And then of course 1 times anything is just that thing back, and you'll also notice that you've got an x to the -1 plus a negative x to the -1, so those add to 0, and the whole thing ends up simplifying fairly nicely to just 1 minus x to the -2. Now I've told you several times already, I'll tell you a bunch more times, WebAssign doesn't necessarily force you to simplify it all the way down, so you might be able to get WebAssign to accept an answer maybe even back at that step. The advantage to that is you don't have to do so much simplification. The disadvantage to doing it that way is that even if it will accept the answer in a more complex form, the fact that it's more complex means there's more chance of making a typing mistake as you're typing it in. So you have to balance those risks yourself, and you've got to play around with it and decide which way works best for you. I can't do that for you. Again, I mentioned all the little algebraic things that can cause you trouble, trip you up. I'm not going to dwell on them here, but just be sure that if you have any of those deficiencies that you handle them, because they will cause you problems in this course. Not only would I say don't ignore it, but don't wait too late, even if you decide later that you're not going to ignore it, because by then it may be too late. It's really a big mistake not tackle these issues early on and handle them before your grade suffers. Another example. Here we've got 3 products. Now we don't have a product rule that deals with 3 products. Our product rule says, here's what you do if you have a factor times another factor and you want the derivative. But there's a way around that, and my suggestion is take the 2 simplest factors and multiply them together and simplify that, and then you'll have 2 factors. So since we don't have a 3-factor version of the product rule that we've developed or derived, instead take the 2 simplest products, multiply it out, and then that'll give you the 2. So the 2 simplest products are x plus 2 and x minus 1. If you multiply them together and FOIL them out, you'll get x squared plus x minus 2. So again, another illustration of why you need to have pretty decent algebra skills. So now if you rewrite that so that those 2 simpler factors are multiplied together, you now have something that the product rule applies to. The 2x squared plus 1 is like the u, and the x squared plus x minus 2 is like the v, and you can use the product rule. The product rule says the first one times the derivative of the second one plus the second times the derivative of the first. Those are both very easy derivatives to take, so I'm not going to emphasize that too much here. That's something you need to do when you're alone working through these problems yourself. It might be that you can type your answer in just like that and WebAssign will accept it, but you've got to decide if you want to do it that way or simplify it more, because if you don't simplify it, there's much more chance that you'll make a typo as you're typing it in. I'm going to go ahead and simplify it. If you multiply the first 2 factors together and FOIL it out, and you multiply the second set of products by multiplying through by 4x, and collect like terms, you'll get that the derivative is 8x cubed plus 6x squared minus 6 plus 1. Like I said, you might find that WebAssign accepts the answer way back up here, and that you can type it in very nicely without having any errors. And if you decide that you can do that and want to do that, then that's perfectly legitimate. That's a decision you have to make. But you need to practice. I want to say too that the product rule is generally used only when both the factors are variable quantities. If one of the factors is just a number, you generally use one of the other rules instead. And we'll talk about that more when we come to a really good example of that. You could use the product rule even if one of the factors was a a constant, but you generally won't be doing that. On the other hand, for some exercises, there are at least two very reasonable ways that you can do this and get an answer. And you've got to, again, decide from practicing which way is more reliably correct when you work it out, and then stick with that method. A simple example, if you had y is equal to 2x times the quantity x squared plus 3x, if you just apply the product rule directly, you've got the first factor times the derivative of the second plus the second factor times the derivative of the first, and those two derivatives are extremely simple. And then if you multiply out the parentheses in those two terms and collect like terms, you'll end up with 6x squared plus 12x. But you could decide, well, I'm just going to multiply it out before I even start. It's not bad at all. And if you do that way, you'll find you'll get exactly the same answer, probably with less work. But you have to practice doing these things and decide which way makes most sense to you. I cannot make that decision for you. Now, what about quotients? We talked about products. The product rule isn't as simple as it could be, but it's not so bad. The quotient rule is not as simple as you might hope it would be, and it's a little bit worse than the product rule. If you've got two differentiable functions f and g, as long as g is not 0, the quotient f divided by g has a derivative that's equal to g times the derivative of f minus f times the derivative of g, all of that divided by g squared. Well, that's a mouthful. Symbolically, you could write something like this. The derivative of f of x over g of x would be g of x times f prime of x minus f of x times g prime of x all over the square of g of x. Or if you just want to think numerator denominator instead of f and g, you could also think of it like this. The derivative of the numerator over denominator is denominator derivative of the numerator minus numerator times the derivative of the denominator all over the square of the denominator. I have found over the years that students have a particular problem remembering the quotient rule right, so I'm going to give you one more thing. This might help, and if it does, use it. If it doesn't, then stick with one of the things we've already talked about. If you talk about high, low, high being numerator, low being the denominator, you can write the quotient rule as low times the derivative of high minus high times the derivative of low over low squared. Now, the reason I wrote it that way is it generates a memory aid that you can say. And if you think that helps, then that might be a good way to remember it. The memory aid might be something like this. The derivative of high over low is low d high minus high d low over low low. And in that context, d high means the derivative of high, and d low means the derivative of low, and low low means low squared. So if that memory aid helps you, there you go. The derivative of high over low is low d high minus high d low over low low. Use it if it helps. Now, if we combine all our previous derivative rules with this quotient rule, we now can differentiate any rational function. And so why don't we just jump into doing one of those? If I ask you to find the derivative of this rational function, all you have to do is apply low d high minus high d low over low low, high being the numerator, low being the denominator, low d high minus high d low over low low. And then simplify those two very easy derivatives in the numerator. WebAssign might very well accept that answer right there if you type it in carefully. Or maybe you could multiply the minus 3 by the minus sign and make it plus 3. Anyway, I'm going to go ahead and simplify it. If you want to play around with how simplified WebAssign will let you get by with on your answers, that's your call. But if you multiply out, use the FOIL method on this one, first outer, inner, last. And then over here you multiply by the minus 3, being really careful with your signs. And then you distribute the minus sign here and just keep simplifying. you'll get a reasonably simple solution. The numerator is minus 6x squared plus 8x plus 1. The denominator is the quantity 2 minus 3x squared. If you want to experiment around with whether Webbelstein will accept an answer in a less simple form, you need to do that when you're doing your problems. I do want to point out before I leave this that a common error happens right along in here because there are so many minus signs. Take your time, be careful, write every step out one step at a time, and pay special attention to sign mistakes. Practice makes perfect. Now I could ask you another question once we got the derivative. I could ask something like this. What if we want to find the value of the derivative at a particular point? In this problem, I'm asking about the point 1, negative 1. What you'll notice is that the derivative is what we just calculated, and in order to calculate the derivative, all you need to know is the x value. So all we need to know is this value right here, the 1. So just plug 1 in, be careful with the arithmetic, and you'll come up with 3. So the derivative of that function at the point 1 comma minus 1 is 3. Taking it back to what we talked about earlier, the derivative is the slope of the tangent line of the curve. So another thing you could say here is that at the point 1 comma minus 1, the slope of the tangent line to this curve is 3. Now, not every quotient needs to be differentiated by the quotient rule. Sometimes you could, especially with these fairly simple quotients, you can rewrite them and use a different derivative rule and be better off. But again, that's a decision you're going to have to play around with yourself. For example, what if I gave you y equal x squared plus 3x over 6? Now, certainly you could use the quotient rule on that if you wanted to, but my suggestion is to rewrite that by realizing that dividing by 6 is the same as multiplying by 1/6, and then if you multiply through by the 1/6, you get a very simple function that you can take the derivative of by just using the power rule on each term. So you get 2 times 1/6 x, and then the derivative of 1/2 x is just 1/2, and of course 2 times 1/6 is 2/6, which is 1/3. How about this one? Again, you could use the quotient rule. My suggestion is to think of that as 5/8 x to the 4th, and then just use the power rule. So you've got 4 times 5/8, and drop the 4 down to a 3. 4 times 5/8 is 20/8, which reduces to 5/2. So you have 5/2 x to the 3rd. One more, if you have 9 over the quantity 5x squared, again, you could use the quotient rule. It will work. My suggestion is to think of that x squared in the denominator as an x to the minus 2 power, and then use the power rule, and you'd have minus 2 multiplied by 9/5, and then you subtract 1 from the minus 2 and make it minus 3, and minus 2 times 9/5 is minus 18/5, x to the minus 3. As I said, every single one of those could be done by the quotient rule, and if you're more comfortable doing that, then that's fine, but here are some alternatives if you're so inclined. How about this? This is just a classic, straightforward quotient rule. Numerator, denominator, high, low, however you want to say it. So you take low d high minus high d low over low low. Well, the derivative of the numerator is 2x, and the derivative of the denominator is 1. And then if you clear your parentheses in the numerator, you get a very simple expression with a common, with all the common terms combined. And that's about as simple as you could possibly write it. That's just a classic, straightforward quotient rule problem. Let's end on an application problem. As blood moves from the heart through the major arteries out to the capillaries and back through the veins, the systolic blood pressure continuously drops. Consider a person whose systolic blood pressure P in millimeters of mercury is given by the equation P equal to, in the numerator, 25t squared plus 125 over the quantity t squared plus 1, and that's defined between 0 and 10 for t, and t is measured in seconds. The question is, at what rate is the blood pressure changing 5 seconds after the blood leaves the heart? So we're looking for a rate of change. That's a derivative. So that means we want to take the derivative of this quotient. So we use the quotient rule. Straightforward application, high D low minus low D high over low low. Multiply through the parentheses, being really careful about this minus sign right here. Simplifying the numerator, you'll get negative 200t over the quantity t squared plus 1 squared. That's the derivative. The question asks about what happens when t is 5. So all you need to do is plug 5 in, and you'll find out that the answer is negative 1.48. And again, they said that was in millimeters of mercury per second. Practice is the key. Practice, practice, practice. Look at problems, decide if there's more than one practical way to work them, which way you'll work them, decide which method you're going to use there, decide how much you're going to try to simplify your answers before you try typing them in. All that requires a lot of work on your part. It's nothing I can do to help you with that. It's something you have to do for yourself.